Hi, Mr. Darren. I am Tong. The topic which is assigned to me is linear transformations. In this presentation, I would like to first give some brief background introduction about my topic. After this, I will discuss about an important theorem related to this topic, which is a linear transformation is Lipschitz. When discussing this theorem, I will talk about the idea behind the proof of this theorem, as well as explaining why this theorem is important. And in the last section of my presentation, I will be talking about an example where linear transformation is used. Now, let's begin this presentation. A linear transformation is a special kind of function that is very common, well-known, and useful in the world of mathematics. Based on the mathematical analysis textbooks, a function t from the n-dimensional real space to the m-dimensional real space is considered a linear transformation if, for any vectors x1 to xk in the n-dimensional real space and any scalars c1 to ck in real number, the function t of the linear combination c1 x1 plus until ck xk is equal to the linear combination of the function t applied to each vector separately multiplied by their respective scalars. Linear transformation consists of several properties. For instance, every linear transformation t from the n-dimensional real space to the m-dimensional real space can be represented by a real m times n matrix A. If x is a vector in n-dimensional real space, then the linear transformation of x can be written as linear transformation of x equal to matrix A multiplied by column vector x. Besides, every linear transformation is a Lipschitz function. Hence, this implies linear transformation is continuous and also uniformly continuous. Linear transformation is a very vital concept in many fields such as mathematics, engineering, economics, computer graphics, as well as data science. Linear transformation is very useful as it is widely used in many areas. For example, in mathematics, determining the continuity of a function can often be simplified by verifying that the function is a linear transformation, since all linear transformations are continuous. Besides, in economics, linear transformations are used in econometrics for modeling economic relationships and analyzing data. On the other hand, in computer graphics, linear transformations are used to perform operations such as translation, rotation, scaling, and shearing of objects. These transformations are essential for rendering scenes and animations. Apart from that, in engineering field, linear transformation model various physical systems and processes. For instance, they are used in signal processing, control system, and structural analysis. Lastly, in data science, techniques such as principal component analysis (PCA) use linear transformation to reduce the dimensionality of data. This enhances visualization and interpretation. Next, let's discuss on a vital theorem which is related to linear transformation. That is, a linear transformation t from the n-dimensional real space to the m-dimensional real space is a Lipschitz function. Now, let's discuss the idea behind the proof of this theorem. When discussing this proof, I will use red color highlight to indicate the part of the proof which I am explaining, so that you can easily follow the flow of my proof. We start the proof of this theorem by assume a function t from the n-dimensional real space to the m-dimensional real space be a linear transformation. Then, we let A be the m times n matrix which represents t. So, we have the equality linear transformation of vector x equal to matrix A multiplied by column vector x. We let x be a vector in n-dimensional real space. By fact, we learn from linear algebra, we have the equality as shown on the slide, which is the square norm of tx equals to the square norm of ax. The square norm of ax is then equal to the transpose of ax multiplied by ax. And the transpose of ax multiplied by ax is actually equal to the transpose of x multiplied by transpose of a times a multiplied x. So, what we know from this equality is that square norm of linear transformation of x is actually equal to transpose of x multiplied the transpose of A times A multiply X. By linear algebra, we also know that the matrix A transpose times A is a positive semi-definite n times n symmetric matrix. This means eigenvalue of A transpose times A are real and also non-negative. Next, let's apply this theorem from our maths analysis textbook to continue our proof. The description of this theorem is: let B be an n times m symmetric matrix, and let lambda 1 be the smallest eigenvalue of B, and lambda 2 be the largest eigenvalue of B. For any vector y in n-dimensional real space, lambda 1 multiplied by square norm of y will be less than or equal to y transpose multiply matrix B multiply y. And y transpose multiply matrix B multiply y will also be less than or equal to lambda 2 multiplied by square norm of y. So by this theorem, we have x transpose multiply A transpose times A multiply x must be smaller than or equal to lambda max multiply square norm of x, where this lambda x in here is the largest eigenvalue of A transpose times A. The equality which we obtained from the beginning of the proof tells us that the square norm of linear transformation of x is actually equal to transpose of x multiply the transpose of A times A multiply x. So, for any vector x in the n-dimensional real space, we have square norm of linear transformation of x must be smaller or equal to lambda max multiply square norm of x. This implies norm of linear transformation of x is less than or equal to square root of lambda max multiplied by norm of x. This follows that for any vectors u and v in n-dimensional real space, norm of t of u minus t of v, which is equal to norm of t of u minus v, will be smaller than or equal to square root of lambda max multiplied by norm of u minus v. The first equality here is due to t is a linear transformation. So this shows that the function t satisfies the condition of Lipschitz function, and therefore the linear transformation t is Lipschitz with Lipschitz constant square root lambda max. Next, I would like to briefly talk about the importance of this theorem. In mathematics, this theorem can be used to imply that a linear transformation is continuous and also uniformly continuous, because a Lipschitz function is always uniformly continuous. Hence, this ensures that the linear transformation consists of many nice properties of continuous function, such as the preservation of limit. Besides, the continuous properties of linear transformation also enable linear transformation can be studied by many well-known theorems, such as intermediate value theorem and also the extreme value theorem. On the other hand, the process of determining whether a function is continuous can often be simplified by verifying that the function is a linear transformation, since we know that all linear transformations are Lipschitz functions which are continuous. Next, I am going to enter the last section of my presentation, which is discussing an example where linear transformation is used. An example where this topic is used is in determining whether a function is uniformly continuous. This can often be simplified by verifying that the function is a linear transformation, since all linear transformations are Lipschitz functions which are uniformly continuous. Now, let's prove that the function f from R2 to R2 defined by fxy with first component of 87x plus 100y and second component of 93x minus 32y is uniformly continuous. Instead of trying to use the traditional way which use the definition of uniformly continuous and find the delta for each epsilon, which sometimes can be quite complicated, we can use an easier approach to solve this problem, which is showing that this function is linear transformation. Now, let's show that this function is a linear transformation. Again, I will use red color to highlight the part where I am explaining. Consider the vectors x1 to xk in two-dimensional real space and real number scalars c1 to ck. Then we let xj be defined as pair of elements wj, yj for each j from 1 to k. Then the function f applies to the linear combination of the vectors x1 to xk with the coefficient c1 to ck is equal to the function f applied to linear combination of the vectors w1 y1 to wk yk with coefficients C1 to Ck. Then we can multiply each scalars into their corresponding vector. This is equal to the function f applied to the pair where the first element is the sum of C1W1 through CKWK and the second element is the sum of C1Y1 through CKYK. The function f then evaluates to a new pair, where the first element is 87 times the sum of C1W1 through CKWK plus 100 times the sum of C1Y1 through CKYK, and the second element is 93 times the sum of C1W1 through CKWK minus 32 times the sum of C1Y1 through CKYK. Next, we distribute the constants inside the sum. We have the first element as the sum of C1 times 87 times W1 through CK times 87 times WK plus the sum of C1 times 100 times Y1 through CK times 100 times YK. And the second element is the sum of C1 times 93 times W1 through CK times 93 times WK minus the sum of C1 times 32 times Y1 through CK times 32 times YK. Due to the limits of page, I will move the final row to the next page. Now, we continue from the row we stopped from the last page, which is the part I highlighted in red. After changing the order, we get the following. Then, we can separate this vector into summation of vector with the same scalar. Next, we can factor out the scalars for each vector. Now, we can observe that each vector now is actually the function f applied to the pair wjyj for j from 1 to k. So, this is equal to the sum of c1 times f on w1y1 up to ck times f on wkyk. Lastly, this is actually equal to the linear combination of the function f applied to each vector x separately multiplied by their respective scalar. Since we have successfully shown that the function f of the linear combination c1x1 plus until ckxk is equal to the linear combination of the function f applied to each vector separately multiplied by their respective scalars, f is therefore a linear transformation. This implies f is a Lipschitz function. Due to a Lipschitz function is always uniformly continuous, f is uniformly continuous. In short, concept of linear transformation is very vital in this kind of situation because by determining that the function is linear transformation, we can solve the problem easily. This is all for me today for my presentation. Thank you for spending your time to listen to my speech. I really hope that you can enjoy it. And last but not least, I wish you have a nice day. Bye bye.